we can actually start with a new Schrödinger equation, but instead take some of the stuff that looks like this and put it in. So So if we start with a Schrödinger equation like this, then we do the same thing we did here, but I'm going to skip all this stuff. And we do this transformation. And I'll just tell you now, this is what's called a gauge transformation. And once we plug all this in, this ends up giving us these transformation rules. Well, we plug this stuff in, solve out the Schrödinger equation with this stuff, plugging it all in the partial derivatives, and we end up with, after we do the transformation, A goes to A plus del of P, and V goes to V minus the partial derivative of P of x and t. And then it's kind of clear from this that this is a vector potential and a scalar potential. And like if you're in E&M with me, you might actually recognize that crap. So then from there, we can look and plug these back in, and these actually preserve all this. They preserve the inner product in the Schrödinger equation. So it validates our physics to use this stuff. And these are also end up being the transformations, the gauge transformations that define our electromagnetic field. So if you look briefly, I'll just prove it for the magnetic field unless you want to see it for both, but it's likewise. So, if you recall, the magnetic field equals the gradient for del cross A. But then we'll call this A prime, the transformed one. So we'll plug A prime in. So B should still be this gradient if it's preserved. So what you end up getting is, when you plug in the A prime, you get del cross A plus del cross the curl of P. So then the gradient, the curl of the gradient, which is 0. So this just ends up giving us back the magnetic field. So that preserves our laws, and you can prove that likewise using the definition that E So using this definition for the electromagnetic field, you can just plug in the vector potential again, and you recover the same thing. So starting from there, that's, I guess, how you can see when you do these gauge transformations in a Schrödinger equation, it preserves physics in an otherwise unpreservable situation. And these are actually end up being derived by what's called the Coulomb gauge, which is just, it comes from requiring the fact that del dot A equals 0. In relativistic cases, you use a Lorentz gauge or a Landau gauge. Landau gauge we're going to see later in solving for the quantum Hall effect. And that's given by the covariant gauge. And this A upper mu is defined by 4 vector, where A is the vector potential, and this phi is actually, it's a scalar potential, same as B. So that's going to come up in how we solve for the Hall effect. I guess if you have questions along the way, you can ask. Now I get to use an overhead projector. Ask your grandpappy about this.